This video describes new procedures in Statgraphics Centurion version 20 for machine learning. Version 20 adds 10 new procedures for supervised machine learning. Supervised machine learning is used for predictive analytics, where algorithms are trained on a set of data with known outcomes in order to predict similar data with unknown outcomes. Supervised machine learning algorithms are validated either by withholding some cases to create a test dataset or by cross-validation. The 10 machine learning algorithms added to version 20 are shown here. They include decision forests and decision trees, discriminant analysis, Gaussian processes, gradient-boosted trees, linear models, naive Bayes, nearest neighbors, neural networks, and support vector machines. A wizard is available to help select the best algorithm for any given dataset. Users need to specify the data for the algorithms only once and can then run multiple procedures. Predictions may be created based on the best model or using an ensemble prediction based on multiple models. The machine learning algorithms in Statgraphics use the Statgraphics Python interface. The data are entered into Statgraphics. Procedure options are set using Statgraphics dialog boxes. A script is then sent to the scikit-learn library in Python, which executes the algorithms and returns the results. The results are then displayed as tables and graphs in Statgraphics. The first example I'm going to show is a typical classification problem. It involves data from the University of California, Irvine's machine learning repository. The file contains information about breast masses found in 569 women. Some of the masses were eventually diagnosed as being malignant, others as benign. The goal is to come up with a procedure by which we can classify an unknown mass as being either malignant or benign based upon various measurements of the mass without having to do a full biopsy. In a machine learning problem, the variable that we want to predict is called the target. In the sample file, it's in a column called diagnosis. B indicates that the mass was eventually found to be benign. M means that it was malignant. In the sample dataset, there were 357 benign masses and 212 malignant masses. The variables that will be used to predict the target are called features. In this case, 30 features will be used to predict diagnosis. These include the mean, standard error, and worst measurement of 10 characteristics of each mass. The characteristics are the radius, texture, perimeter, area, smoothness, compactness, concavity, concave points, symmetry, and fractal dimension. In Statgraphics, the machine learning procedures are contained on the main menu under Learn. Here you see a section with 12 supervised learning procedures. 2 use the interface with R, the other 10 use the interface with Python. There's also an option to use the supervised machine learning wizard. A commonly used supervised machine learning algorithm is the decision tree. A tree predicts an unknown outcome by traveling down the tree which consists of nodes and branches. At each node, you can move along either a left or a right branch, depending on the value of a single feature. You can control the complexity of the tree in various ways, including specifying the minimum number of observations at each node. If you select Decision Tree from the Learn menu, you'll see a dialog box used to specify the data. The first item you need to specify is the column containing the target, in this case, diagnosis. The second thing you need to specify is whether this is a classification problem or a regression problem. In a classification problem, you want to predict the category of the target variable. In the case of a regression problem, you're trying to predict the numeric value of the target. The features may be combinations of both categorical and quantitative variables. In this case, all 30 of our features are quantitative. You may specify a column of weights if you want to give more weight to certain rows in your data file than others. And you can use the typical select field if you only want to consider a subset of the rows in your datasheet. When running a supervised machine learning algorithm, you need to define 3 sets of data. The first set is the training set. These are observations that are used to train the algorithm. In a decision tree, training means determining which features are used to define each branch of the tree. The second set of data is a test set. These are observations for which the target value is known, but which are not included in the training set. The reason for doing this is to determine objectively how good the trained algorithm is at predicting observations which were not used to train it. The test set is not needed if you're doing cross-validation. The third set is a prediction set. These are observations for which the target value is not known, but you wish to predict it. You're now looking at the dialog box that Statgraphics uses to define those 3 data sets. In the top right, you define the training set. The training set could be all rows in the primary data sheet, that's usually data sheet A, or some subset of those rows. You'll notice below the specification of the training set a couple checkboxes. The first checkbox says fix random seed. If you fix the random seed at a particular numeric value, then each time the algorithm is run, you'll get the same results. This is particularly important if some aspect of the algorithm involves random selection. There's another checkbox by which you can ask it to perform cross-validation. I'll talk more about that a little later, but basically the default is to create 5 folds. That means that I'll train the algorithm 5 times, each time withholding 20% of the data. And then I'll determine on average how well a fit can predict the observations that were withheld on a particular run. The test data set may consist of either all rows in the training data sheet that were not contained in the training set, or all rows in a different data sheet. And finally, the prediction set can be either all rows in the primary training data sheet for which the target value is not known, or it can also be placed in a different data sheet. Each machine learning algorithm has certain options that you specify on the Analysis Options dialog box. In the case of a decision tree, this includes things like the maximum depth of the tree. That's how many levels of branching are allowed. You can also specify things like the minimum number of samples to split a node. There's also an option for the minimum number of samples at each leaf, and one for the maximum number of leaves. These are common options that you might like to change. You'll also notice in the top right a box labeled Standardization. Standardization is used when the features have different units in order to put them in similar scales. For example, standard scaling would take each feature, subtract the column mean, and divide by the column standard deviation. It turns out that decision trees are not impacted by standardization, but for other algorithms, machine learning algorithms, it can be very important. You'll also notice in the bottom left a checkbox labeled Tune Parameters. I'll talk about that in a little while. The final dialog box you'll be presented with lists the tables and graphs that you can create. This will depend on what machine learning algorithm you're using, but it will always contain certain things like the analysis summary, predictions and residuals, and a classification table. Things like the tree diagram, of course, are specific to decision trees. You'll also notice in the bottom left an option to display the Python script and messages. This is the script that's actually sent to Python and any messages that it returns. It can be important to look at that particular table if for some reason the algorithm could not be run on your data. To keep things simple, I've decided to limit the number of branches in the tree to 3 levels. The way you read this is you start at the top where it says Diagnosis. Traveling down, you'll see that the first branch depends upon the worst value of the radius measurement. If the value of radius worst is greater than 16.795, you move right. If it's not, you move left. Suppose you move right. You then look at the worst value of texture. If that's greater than 19.91, move right, else move left. And finally, you look at the worst value of smoothness. If it's greater than 0.08798, move right, else move left. If you move right, you then end up at a leaf, and our prediction is that the mass is malignant. For any mass, you can follow each of the branches down, and you'll end up at a leaf, and the prediction will either be benign or malignant. Once you've created the tree diagram, if you press the right mouse button, you can look at the Pane Options dialog box. There are a number of quite useful options here. The first is the font scaling factor. If the tree is complicated, you'll want to use a number less than 1, like 0.5, to reduce the size of the text. That will minimize the amount of overlapping. Another option that's useful is rotating the leaf labels. that will take the label at the bottom of the tree for each leaf and turn it vertical instead of horizontal. And finally, it can be quite useful to include with the leaf not only the prediction, but also the probability associated with that particular prediction. Here's a version of the decision tree where I've added the prediction probabilities. You'll notice for each leaf, it'll say things like P equals, the far right leaf says 0.99. That means that 99% of all the training cases that arrived at that leaf were malignant, were correctly predicted. On the other hand, 100% of all the training cases that arrived at this leaf here were correctly predicted to be benign. Adding the prediction probability shows how well my algorithm can differentiate between levels of the target variable. The list of tables and graphs for the decision tree also contains a tree diagram created by Python. This diagram has additional information at each node of the tree. For example, at the top node, you see all 569 samples in the training set. The branch to the left is defined by radius worst less than or equal to 16.795. At this particular location, the Gini coefficient, this is at the very beginning, is 0.468. Now the Gini coefficient is a measure of inequality. If all the observations were the same, all the masses were benign or all malignant at that particular node, Gini would be 0. It's on a scale of 0 to 1, and basically the closer it is to 0, the more homogeneous the samples. Well, at this particular location, 357 of the training cases were benign, 212 were malignant. So if you stopped at this node and had to make a prediction, you'd predict benign, because more samples at that node are benign than malignant. Now, once you take the first branch, let's say to the right, you find the Gini coefficient went down quite a bit, down to 0.109. That's because 190 samples that went to this node contained 11 benign masses and 179 malignant masses. Of course, if you had to make a prediction at that point, you'd predict malignant. And you can continue and notice at each of the nodes, the Gini coefficient continues to get smaller as you go down. So if you get all the way to the bottom right, the Gini is 0.019 because of the 172 masses that made it all the way to the bottom right, 171 were malignant. It's a very interesting tree diagram with a lot of information. An important table to look at when running the machine learning algorithms is the analysis summary. This shows the settings of the model, what options were selected, such as the maximum depth of 3 in this case. It also shows the results. In the case of a classification problem, it shows the percentage of the training cases that were correctly classified. In this case, a total of 97.891% of the training cases, the 569 cases, were correctly classified by the tree. Now, it also gives a statistic for cross-validation. Cross-validation is used to try to show how good this tree would be in predicting observations not used to actually train the tree. To validate its machine learning algorithms, Statgraphics uses five-fold cross-validation by default. With five-fold cross-validation, you divide the training set into 5 equal-sized subsets. You then run your algorithm 5 times, each time withholding one subset. The resulting statistic is the average of the percent of withheld cases correctly predicted across the 5 runs. Another important table to look at is the classification table. This table shows the percentage of false positives and the percentage of false negatives. For example, there were 357 benign masses. Of these, 4 were predicted to be malignant. That's a false positive rate of 1.12%. Of the 212 malignant masses, 8 were predicted to be benign. That's a 3.77% rate for false negatives. As I pointed out earlier, the Analysis Options dialog box contains a checkbox labeled Tune Parameters. If you check that box, the program will try various combinations of 4 model parameters: the split criterion, the maximum tree depth, the minimum impurity decrease, and the pruning complexity. That means it'll take a total of 3 times 4 times 4 times 4 combinations of those parameters and tune the model using all of those combinations. It will then keep whichever combination of the parameters gives the best cross-validation result. This table shows the parameters selected during tuning. One change was that it changed the split criterion from Gini to entropy. It also changed the maximum depth of the tree from 3 to 5. This resulted in an almost 2% increase in the percent of correct predictions during cross-validation. This diagram shows the new tree. It's interesting to note that the first split at the top now involves a different feature. It's the worst value of the perimeter. This turns out to occur because of a switch from the Gini coefficient to entropy in determining which feature to use to make the split. It's also interesting whenever you use a machine learning algorithm to determine which of the various features has the biggest impact on the predictions. One way to do that is to calculate what's called the permutation importance. What you do is you take each feature one at a time and sort it in random order. You then make your predictions and see how much worse they are than when that feature is sorted in its proper order. In this case, you can see that perimeter worst has by far the biggest impact on the proportion of correct predictions. If you sort it in random order, the percent of correct predictions goes down by 26.6%. This is probably not surprising in this case, since perimeter worst does define the first branch in the tree. Another interesting plot to create is the 2D predictions plot. To create this plot, you pick two features, normally the most important two, and you let each of those features vary over some range. You then fix the value of the other features, often at their average level. What you can see here is that if you look at the perimeter worst and the concave points worst, the mass will be predicted to be malignant if either or both of those features is large. You can also overlay the training set on top of that two-dimensional prediction plot. Now, this doesn't take account of all the other features, but you can see, except on the margin, close to the boundary points, it's pretty clear whether the mass is going to be malignant or benign based only on those two features. Once the machine learning algorithm has been trained, it may be used to make predictions about additional cases where the target value is not known. Here I've added 5 additional rows to the bottom of the datasheet. Those rows have values for all of the features, but the target diagnosis is left blank. In this table, you see the prediction for each of the 5 rows together with its probability of being correct. You also see the runner-up, which might be relevant if there were more than 2 categories of the target, and its associated probability. You can see in this case that there's little doubt about any of those 5 additional cases. I now want to take a couple minutes to describe the machine learning wizard. The wizard is designed to help you select the best algorithm. It's a 5-step process. In the first step, you select the target variable and the features. In the second set, you define the training, test, and prediction sets. The third sets options used by all the machine learning algorithms. The fourth fits one or more machine learning models to the data. And finally, step 5 makes predictions. The big advantage of using the wizard, if you want to fit more than one model, is that you only have to specify the data once. When you select Wizard from the Statgraphics Learn menu, this window will open. It has a toolbar with buttons for each of the 5 steps, plus additional buttons for cloning a model or deleting a model. As you go through the steps, a summary of what you've done will be added to the main part of this window. In step 1, a data input dialog box is displayed, similar to that used for the decision trees. On this dialog box, you specify the target variable, the type of problem, and the features you'd like to consider. In step 2, you define the training, test, and prediction sets exactly as I demonstrated for the decision trees. In step 3, you specify options to be used by all of the machine learning algorithms. There's currently only a single option to set, and that's the number of permutations to use in determining feature importances. When you press the Step 4 button, the program will display this list of classification algorithms. You can select one or more algorithms to train simultaneously. If you check the box labeled Use Default Options, the program will bypass the Analysis Options dialog boxes for each procedure and just take the defaults. If you don't check that box, the program will display each analysis options dialog box as it begins to run that procedure. Select the algorithms you want to use and push train. The wizard will then ask Python to fit each of the machine learning algorithms that you've selected. When it's done, there will be a new analysis window created for each of the algorithms. You can examine each in turn or compare them by going back to the machine learning wizards window. One of the most interesting graphs created by the wizard is a comparison of the models that it has fit. This plot shows you the percent of correct predictions using the training data set and during cross-validation for each of the 10 procedures. You'll note that the best model for cross-validation is the linear models. It correctly predicted 98.1% of all the cases that were withheld during cross-validation. Taking a close look at the linear model and the predictions it makes for diagnosis, you'll see that unlike the decision trees, the decision boundary here is diagonal. This seems to do a better job of making the correct predictions for this data set. It's now time to make predictions. When you press the Step 5 button, the program will display a dialog box listing all of the models that you have fit to the data. You can highlight one or more models to use for making predictions. In this case, I've highlighted the 3 models that did best during cross-validation: the linear models, the neural network, and the support vector machines. If you select more than one model, we say you're making an ensemble prediction. By that we mean that you're taking the predictions from the different models and combining them in some fashion to get a single prediction. Now there are a few options that you need to specify. The first is what sort of consensus you need to even make a prediction. In the case of plurality voting, you'll make a prediction based upon whatever target value gets the most votes, whether or not it gets more than half. In the case of majority voting, you won't make any prediction unless some target value gets more than half of the votes. In unanimous predictions, you won't make any prediction unless all the models agree. Now, when it's doing voting, you can either do hard voting or soft voting. Hard voting gives a single vote to each of the fitted models. Soft voting uses the predicted probabilities from those models. If a particular model, a particular algorithm has a higher probability for its prediction than another, then it will get more weight. And finally, if you want, you can base your model weights on performance on the training set or on cross-validation. All of this is combined then to come up with a single prediction. The final predictions are displayed in this wizard table. It shows the predicted target value given by each of the models. In this case, the linear model, the neural networks, and the support vector machines. The prediction column contains the ensemble prediction, and the rightmost column labeled votes shows the percentage of the votes obtained by that predicted target value. In this case, the percentages associated with the ensemble predictions are all quite high. The Step 4 Fit Model button can be pressed as often as desired in order to fit additional models. You may also press the button on the wizard toolbar labeled Clone Model. This will create a clone of any model so that you can then rerun it after changing some of the analysis options. You can also use analysis options to tune the parameters in order to potentially get an even better fit. In this video, I've concentrated on classification problems. Those are problems where you're trying to predict the category that a target variable belongs to. You could also use the same procedures for doing regression problems. In those problems, you're trying to predict the numeric value of the target. There are just a couple differences that you should note. First off, the statistic used to summarize the performance of the model is R squared, rather than the percentage of correct predictions. R squared is the percentage of the variability amongst the target value that has been explained by the algorithm. It's calculated by comparing the variability of the residuals to the variability of the original target values. The second difference is that only 8 algorithms are available. The naive Bayes and discriminant analysis don't apply to regression problems. And finally, residual plots are available in all of the procedures.